I bet many of you ninjas are eager to find out if this function is continuous at x equals 0. The answer is simple to uncover, but only if you use this nifty trick I'm about to show you. So make sure to stick around as we uncover the solution together. For this function here, notice that it's a piecewise function. We are piecing together two separate functions. You've got this line and you've got this curve. And we want to determine what does it mean exactly to be continuous at x equals 0? And is this function continuous there? This is where I'm sure a lot of you are getting confused, but I want to break this down simply for you and basically say that to be continuous at a value of x, the function has to satisfy three separate parts. And each one's pretty easy. Number one, to be continuous at x equals 0, the output of f of x has to have a value. It must be defined. Part two, not only that, but you have to have a defined limit as you approach x equals 0 for the function. So you can't have some undefined answer. And finally, number three, it brings together parts 1 and 2. So point number 3 is basically saying, not only do you have to have a value defined for f of x when x equals 0, but that value must equal the limit value that you found. Okay, so you're hearing the word limit, and you might be scratching your head wondering, how do I determine the limit at x equals 0 here? Because you're looking at this function, and to your credit, something is going on here that's kind of weird. You have this line that approaches x equals 0, and when you get to x equals 0, you notice that there's an open interval here. The value of -4 isn't quite included in the domain of the line because of this openness. Also, at a different value of f of x, at -6, you then close the interval with this curve. So at a glance, you already see a jump is happening here. And that's a pitfall because if you just look at that and right away say, oh, we're not continuous here, you might get the problem wrong because there are some cases, not covered in this video, where you might visually see a jump, but you actually have continuity. But for here, what I want you to do is to use this really cool trick known as the pencil trick. What I want you to imagine is put your pencil down on the paper, and we're going to be tracing the paper along either the line on the left or the curve on the right. And we want to see, did we have to lift the pencil at any point to jump to a different point on the graph? So you'll see what I mean in a second. To define the limit at x equals 0 for the function, what I like to do here is I like to break this into simpler parts. I want to say, okay, let's find the limit as we approach x equals 0, but from the left. And then I want to repeat it by approaching from the right, and I want to see that I get the same value in both cases. Because for the limit to be defined at x equals 0, you must get the same value when you approach the point from either the left or the right, and neither of them can be undefined. They must be defined values. So what I'm going to start with is I want to approach x equals 0 from the left, and I'm going to use this minus notation here to indicate that. And I want to figure out, A, do I get a value for the limit, and B, if not, then what does that tell us? Okay, so when I approach this x equals 0 from the left, notice that we're dealing with the domain of this line over here when we're to the left of x equals 0. So put your pencil down on the paper and trace that line and get closer and closer, as close as you can, to the point where when x is 0, notice that we're getting really close to an output of -4. But also notice that -4 is not included on the domain of this line because it's an open interval. So what's happening though is something else is going on here. That curve is closing the interval at the point 0, -6. Do you see that? And to get from the line to the curve, as you've been tracing the line and you're just barely to the left of x equals 0, you're still on the line getting really close to a y value of -4, and then boom, right when x is 0, you would have to lift your pencil and jump to a y value of -6. This is jump discontinuity, and what that is telling us is that the limit for the function when you approach x equals 0 from the left is not defined. And we could stop here because that already gives us an idea of what the final answer is, but for the sake of showing our work and for understanding, let's go on. So we know that the limit approaching 0 from the left is undefined, and what I want to do now is repeat this for the right-hand side. And before I go on, if you are enjoying this video and it's providing value for you in your homework, be sure to smash that subscribe button and ninja kick that like button. So for the limit going to the right, or I should say approaching from the right of this function, What that's going to look like is we are now on this curve instead, right? Pun intended. So imagine your pencil's on the curve. You are approaching from right to left, this x equals -0, getting closer and closer to that closed value at 0, -6. And at a glance, many of you might get this part wrong, and it's totally understandable because it is tricky. You might be thinking, hey, Dave, when I get to x equals 0, aren't I hopping over to this y value of -4? And doesn't that mean that the limit doesn't exist? But check this out. The value of -4 at x equals 0 is open. So right when you get to x equals 0, when you close the interval using that curve and you land at a point of 0, -6, the function is defined there. And at the same time, you are not jumping to the y value of -4 because that is not on the actual domain of x equals 0. It's an open interval there. So you actually do have continuity when you approach x equals 0 from the right, because not only did the limit value approach to a value of -6, but the function is actually defined there because we have this curve closing the interval at x equals 0. So in the case of approaching from the right, we do in fact have a defined value of -6. Okay, so bringing this all together, what does this tell us? Well, if the limit of the function when approaching 0 from the left is undefined, and when it's approaching from the right, you get -6, we know now that the limit does not exist because two conditions have to have been true. We had to have had a value for both, and already the first one violates this, and the value had to have been the same for both cases. And if the limit is not defined at x equals 0, that violates one of the three conditions to have continuity at x equals 0, which means we do not have continuity.